How much heat is absorbed by a 25.0 gram sample of gold at 25 degrees Celsius when it is immersed in boiling water? Specific heat capacity of gold is 0.128, and specific heat capacity of water is 4.184. And so what I would know here is I would know that we have the gold, and I would know that we would have the water as well. And so in order to solve for this 0.240, what I would know is I would know that my mass of this is equal to 25.0 grams. I would know that the temperature initial was equal to 25 degrees Celsius, and I would know that the specific heat capacity was 0.128 joules over gram degrees Celsius. And then in terms of the water, the only real information I know about the water is that the specific heat capacity is equal to 4.184. And then I also know that this is at a boiling temperature as well. And so what I would know then is that the temperature initial would also be equal to 100 degrees Celsius. Okay. And so what I would want to do then is, because this gold is being immersed into the water, I would know, or I would try to assume, that this temperature here, this 25 degrees Celsius, because it's being immersed in the water, it is going to raise up to 100 degrees Celsius. And so what I would know then is that the final temperature is equal to 100 degrees Celsius, which is the same as this value here. And then so solving for this, I would have Q is equal to mc delta T. Q in this case would be, the mass was the gold, so that was 25 grams. C was 0.128. And T in this case, we said it would raise up to 100 degrees Celsius. So 100 would be our final temperature, 25 would be our initial temperature, and we'd end up with an answer of 240 joules. And that is the exact same thing as 200 or 0.240 kilojoules. Those are the exact same thing there. Again, sorry for that little break there. So that was example number 3. Again, the weird assumption here was that you had to assume that the gold is going to jump up to the same temperature that the water has. And we were also told that in this question that heat would be absorbed, and so we would know that the heat would be absorbed from the 100 degrees Celsius water. Example number 4 here says a piece of stainless steel of mass 25 grams at 88 degrees Celsius is being placed in a calorimeter that contained 150 grams of water at 20 degrees Celsius. If the temperature of the water rose to 21.4 degrees Celsius, what is the specific heat capacity of the stainless steel? So in terms of the steel, what we know is we know that the mass is equal to 25.0 grams. We know that the temperature initial was equal to 88 degrees Celsius. We also know that we're trying to solve for this C. We actually don't know what the specific heat capacity is, and we want to solve for that. And then we know a bunch of pieces of information about the water. We know that there is 150 grams of that water. We know that the temperature initially was equal to 20 degrees Celsius, and we know that the temperature final was equal to 21.4 degrees Celsius. And so what a common or what a known fact that we have to assume is we have to assume if the water changed to 21.4 degrees Celsius, the steel is going to meet it there. And what that means is the steel will actually cool down to 21.4 degrees Celsius. So that was the assumption. That's the key assumption here that we have to make, is that those two temperatures will be identical. And then we know that the C is 4.184. So setting this up, we have more information in this question than we do the previous one. So we want to set up that the Q of the system is going to be equal to the negative Q of the surroundings. So plugging these values in, I would want to put mc delta T is equal to negative mc delta T. And in this case, I would plug in for my steel the 25 grams. My value of C that I would plug in, I don't know. I want to figure that out. My delta T in this case will be 88 minus 21.4. And then on the other side, I would have 150 grams, 4.184, and my delta T would be 21.4 minus 20, like that. And then I'd start to solve for this. So I'm going to simplify this side a little bit. I have 25 grams, question mark, and then in the brackets, I can simplify that to be equal to 66.6. And that will be equal to negative 150 times 4.184 times bracket, I guess that would be equal to 1.4. So I know that this right side is equal to negative 878.64. What I would want to do then is divide 66.6 from both sides. And I'd also want to divide 25 from both sides. Divide 25 from both sides. And what we'd end up with is the question mark, which we had said was our specific heat capacity, or C, of the stainless steel. So C of the steel is equal to 0.528. 0.528 joules over gram degrees Celsius, which is exactly what the PowerPoint revealed to us here. Okay. Yeah. The question mark is just, yeah, I can plug C in for that. Why don't I do that? Yeah. There you go. All right, so that's example 4. Example 5 here. What is the mass of a piece of graphite? So I'm going to start writing down my information that I know already. So I have graphite. What is the mass, is the question that I've been asked, of the piece of graphite, which has a specific heat capacity of 0.71, and the temperature initial at 92 degrees Celsius. If it was placed in a calorimeter that contained, well, we're dealing with water again, calorimeter that contained 200 grams of water at 12 degrees Celsius. So the temperature initial was 12 degrees Celsius. The temperature of the water rose to 16.8 degrees Celsius, and the specific heat capacity of water is 4.184. So again, if we know that the temperature of the water is rising to 16.8, we're going to assume that the temperature of the graphite is going to fall to 16.8 degrees Celsius. Again, the whole point of a calorimeter is to have heat exchange where two things are becoming the exact same temperature. So we should be able to solve for this then. Again, we're going to say that the Q of the system is equal to the negative Q of the surroundings. So MC delta T is equal to negative MC delta T of the water and of the graphite respectively. Plugging in some of our values, we don't know what the mass is. We would like to solve for that. We know that the C is 0.71. We know that the delta T is 92 minus 16.8. And we're going to set that equal to negative 200 grams times 4.184 times 16.8 minus 12. We can simplify these a bit. Here we end up with mass times 0.71 times 75.2 is equal to 200 times 4.184 times 16.8 minus 12 bracket is equal to, that's a huge number, 4,016.64. And again, we want to do what we did last time, which was divide by 75.2 and divide by 0.71, divide by 75.2, and divide by 0.71 here. That was the 92 minus the 16.8. Yeah, that was the temperature there. And when you do, you end up getting an answer for a mass of 75.2 grams. So again, the key assumption that we've been making each time here is that these final temperatures, and this is based on what we talked about the last two lessons yesterday, that these two temperatures will be equal. So again, we made those assumption here about the two final temperatures. We were told what the water went to, but we weren't actually told what the graphite went to. And so we assumed that when the temperature settled out, they would both be equal. So we got one more example that we're going to try, and this one is a little bit more tricky. We have a 65 gram piece of iron, so I'm going to write iron here. Our mass is equal to 65 grams. We have a 65 gram piece of iron. We're given the specific heat capacity of 0.449, and it is placed at a temperature initial of 525 degrees Celsius. Okay, and then we are also told that it's placed into water. We're told that it's placed into water, and we are told that the mass of the water is 635 grams. We are told that the mass of the water is 635. We're told that the temperature initial is 15 degrees Celsius. We're assuming that it's at 15 degrees Celsius, so it is a liquid. So we will use 4.184 as our value for C again. And then in both sides of this equation, we actually do not know what the final temperature would be. So this will require a little bit more arithmetic to try and solve this question. But we're going to set it up the exact same way. We're going to say Q of the system has to be equal to negative Q of the surroundings. And so again, that means that MC delta T will be equal to MC delta T, negative MC delta T. And we can start to plug in some of our values. Our mass of the iron was 65 grams. The value for C was 0.449. The temperature initial, so we're going to plug in TF minus temperature initial was 525. And we know that that should be equal to our mass, negative 635. We had a C of 4.184. Temperature final, we don't know, but we do know that the temperature initial was 15 degrees Celsius. And so this is where we can actually solve this question based on the previous assumption we had been making. We had been making the assumption that the temperature final of both of the two components that we're using must be equal. And so what I know is that this TF, whatever number that is exactly identical to this TF over here. And so what I'm going to do is I'm going to simplify a little bit. 65 times 0.449. That leaves me with 29.185 times TF minus 525. I'm going to leave that stuff in the brackets for now. And then on the other side, I have 635 times 4.184. I have a value of 2,656.84 times TF minus 15. And now what I'm going to do is I'm actually going to FOIL out these brackets. So I'm going to take that times that, and that times that, and same thing on the other side. I'm going to take the number outside the brackets and multiply it by both things inside the brackets. So I'll end up with 29.185 TF, whatever that value is, minus 525 times 29.185 minus 15,322.125. And I know that that will equal 2,656.84 TF. And I need a bit more space, so give myself a bit more room here. And I know that from that, I'm going to subtract 2,656.84 times 15, which is equal to 39,852.6. So what I want to do now is get all of the TFs on one side. So I'm going to subtract 2,656.84 TF from both sides, minus 2,656.84 TF from both sides. So I'm going to combine my like terms, 29.185 minus 2,656.84 leaves me with a value of negative 2,627.655. And I still haven't dealt with this 15,000 here. 15,322.125 is equal to now negative 39,852.6. So I'm going to add 15,322.125 to both sides, add 15,322.125 to both sides, and then I'll be looking at this really ugly equation of, I forgot my TF, negative 2,627.655 TF is equal to 39,852.6. I'll be looking at this really ugly equation of 24,530.475. The last step to do here would be to divide by negative 2,627.655 on both sides. Oops, sorry. And I should also note that this is a negative value here. I'm just going to check my work and just make sure that I did all my steps correct here. Oh, yes, that's what I forgot. So here's what I forgot. I forgot that this is a negative value. And so that would make this value negative, this value positive, this would be positive. And so we would be adding on, so this value would change. So I made a mistake with my negative sign. I forgot to include it in, I forgot to include it in this step here and this step here, which changed the sign of this 39,000 to a positive. And so when I add over the 15,000, I'm going to get 39,852.6 plus 15,322.125. And I'll get a value over here of 55.174. And then when I do that, I'll actually get the correct answer, which is that the temperature final is equal to 20.5 degrees. So again, what I forgot, I made kind of a key error, is that I forgot this negative Q surroundings. And so when I was multiplying my 2,656 here by the TF and by the negative 15, I forgot to include that. And so because I forgot to include that, I ended up with entirely wrong values. This negative 2,656.84 remains negative, but this one, when you had a negative value times the negative 15, needed to be positive. And then when you did, all of the rest of the steps are the same. You're just isolating variables and ending up with this TF here. Does anyone have any questions about that example?